Start.
Let me introduce you.
Wait a minute.
Yeah.
Oh, okay. Let me just a sec.
Fine. I'll wait.
Hello, everyone. We are happy to have here Professor Harish Seshadri. He will speak on Yau's uniformization conjecture, part 1. Please go ahead.
Thank you for the invitation. So, as the part 1 says, there will be 2 more talks. In fact, it's whatever I'm speaking about is joint work with Ved Dattar and Vamsi Pingali. And let me start. My talk will be mostly the background to this, the main result. So one of the, I'm not sure exactly what Yau's motivation was for formulating his conjecture, but this might have been one of them. In 69, Gromol and Mayer proved the following quite remarkable theorem. It states that a complete non-compact Riemannian manifold with positive sectional curvature is necessarily diffeomorphic to Rn. Now, this is very interesting because if one looks at compact Riemannian manifolds with the same curvature condition, they're still not well understood at all. Finding examples itself is a non-trivial thing. But on the other hand, in the non-compact case, you get this very strong theorem without even assuming simply connected. That's part of the conclusion. So the natural complex or Kähler analog would be this. That is Yau's uniformization conjecture, the content of all our 3 talks. One looks at complete non-compact Kähler manifolds. Now, for now, I'll assume the same curvature condition, sectional curvature greater than 0. Then the conjecture is that we already know it's diffeomorphic to Rn, R2n by Gromol-Mayer. Now, one would like to ask if it's biholomorphic to Cn. Of course, Cn R2n has lots of complex structures, and it's in fact very complicated. There are very complicated complex structures. So potentially there could be an exotic structure on R2n, which were with this kind of metric. But the conjecture is that there cannot be such a thing. It has to be the standard one. Now, there is some interesting thing going on here, that in the Kähler setting, positive curvature of various kinds have very strong, far stronger consequences than in the Riemannian setting, which is not that surprising. But the interesting part is the dichotomy between compact and non-compact manifolds. In the compact case, again, there is a weak version of a famous conjecture of Frankel, which was, it's still called Frankel's conjecture, though it was settled by Mori and Siu and Yau independently in 1980. So the theorem or conjecture is that a there's a typo here. Obviously, compact, non-compact doesn't make sense. So it should be, if you have a compact Kähler manifold with sectional curvature greater than 0, then M is biholomorphic to a complex projective space. So in contrast, as I mentioned earlier, in contrast, there are examples of compact Riemannian manifolds with positive sectional curvature that are not diffeomorphic to any the standard canonical thing, which is the sphere or a quotient of the sphere. In fact, there are examples which are not diffeomorphic to any compact symmetric space. So on the one hand, in the Kähler case, compactness guarantees a very strong theorem, while the non-compact thing is open, while in the Riemannian case, it goes the other way. The non-compact case can be settled and has been settled, but the compact case is very poorly understood. So I mentioned for both these Frankel's conjecture and Yau's conjecture, I wrote weak version because the actual conjecture is under a much weaker, it's a much weaker version, a much weaker variant of curvature, positivity, much weaker than positive sectional curvature. So let me talk a bit about that. This one, this curvature condition is kind of, it's not so intuitive, but it has proved to be very useful in Kähler geometry. So it's called holomorphic bisectional curvature. So Frankel's conjecture was actually proved under this weaker assumption of holomorphic bisectional curvature being positive. And so here, a Kähler manifold is said to have a positive holomorphic bisectional curvature if for any two real tangent vectors, x and y, we have this Rx. The point is this Rxy, xy, and the other term, Rxjy, xjy, both of these are up to multiples. A sectional curvature of in the first case, it's up to a multiple, the sectional curvature of the two planes spanned by x and y. Here, it's a sectional curvature of the two planes spanned by x and jy. Again, up to multiples, up to positive multiples. So it's in a sense, it's like taking sum of two sectional curvatures of a very specific kind, and we are demanding that it's positive. Now, why one would consider something like this in the first place? I don't have time to go into that, but let's just note that this positivity of this quantity sits in between two classical notions. One is positive sectional curvature, because if that's positive, then both these terms are positive. And one can show that if the sum is positive, then one can, by choosing a suitable orthonormal basis, one can show that the Ricci curvature is positive. So it's a sort of intermediate thing. Now, Frankel's conjecture, as proved by Mori and Seo and Liao, you don't need full sectional curvature, positivity of sectional curvature. Just a compact Kähler manifold with B greater than 0 has to be biholomorphic to CPN. And correspondingly, sort of taking inspiration from the compact case, Yao's conjecture is that, again, you don't need positive sectional curvature, you just need B greater than 0. And then one asks if the underlying manifold is biholomorphic to CN. But the problem is that this very strong theorem of Mori and Siu Yao in the compact case, Mori's proof was it's a purely algebraic geometric proof. He proved that Fano manifolds with ample tangent bundle have to be isomorphic to PN, CPN. And the proof doesn't shed. And Siu Yao used harmonic maps and proved that there are lots of harmonic maps are holomorphic, essentially. Harmonic maps of the two sphere into the manifold are holomorphic, and they got a lot of rational curves, etc. Now, none of these, nobody has been able to adapt either of these to the non-compact setting. So this problem has to be approached entirely separately. And in fact, it's even unknown. So this, while if, as I mentioned earlier, if one had positive sectional curvature, the Gromov-Meyer theorem tells us that the underlying manifold is diffeomorphic to R to N. But if one relaxes to this B condition, B positivity of B, it's not even known. It's if the manifold is even simply connected. So we certainly nothing basically in the non-compact case. It doesn't shed well. No one has been able to use this condition to infer any result about the topology of such manifolds. Though we were able to make a small sort of observation in this area, which I'll mention towards the end, something about the topology of such manifolds. And the other thing is the complex structure. It is, if one had positive sectional curvature, one knows that such manifolds are Stein. So this basically one constructs using distance functions, one constructs a strictly plurisubharmonic exhaustion function. And that's basically equivalent to the manifold being Stein. But if you just work with B greater than 0, one can still construct strictly plurisubharmonic functions, but one loses the exhaustion property, and that makes a very big difference, both for topology and for the complex structure. So again, so let me let me just briefly describe what was known about Yau's conjecture, either the weak version or the full strength version before our work. So in the Gromov-Meyer theorem, perhaps the key ingredient is the existence of a convex exhaustion function on the manifold. Again, as I said, one uses distance functions to do this. Actually, technically, one uses the Boseman function of geodesic rays and constructs a convex exhaustion function on M. And since it's convex, its sublevel sets are contractible or etc. And then one gets lots of information about the underlying manifold. But when we move to the B greater than 0 setting, as I mentioned just a few minutes ago, one gets a strictly PSH function, but it's unclear if it's proper. And in fact, yeah, there's no reason to expect that it's proper in this setting. So as a result, it's very kind of tricky to work with just this condition without any further assumptions. There's basically nothing one can do, no techniques applied directly. So the earlier works on this conjecture have, all of them, without exception, have involved additional assumptions on things like volume growth is one of the most recurring themes. Volume growth, curvature decay, then finiteness of curvature integrals, etc. So these are all global assumptions on the manifold, basically dictating sort of in one way or the other, telling us, assuming something about the asymptotic geometry of the manifold. So let me briefly list some names in this connection. One of the sort of the major work was Mock's work, which basically this is the pioneering work sort of in this area in the late 90s, I think, or 80s. So more than the result itself, he assumes a lot of extraneous, not extraneous, additional assumptions apart from positive bisectional curvature. And finally is able to conclude by holomorphic to Cn, or it's a weaker conclusion is it's quasi-projective. But more than the theorem itself, his strategy has proved to be very influential. And in fact, that's the strategy we follow roughly. So Vogt developed a strategy for realizing such manifolds as quasi-projective varieties. So his tools and overall scheme have been used by multiple authors since. This was the pre-Ricci flow era. And then around 2000, Albert Chow and others use it's natural to try to use the Kähler-Ricci flow, starting with the positively curved metric, and hope that eventually it will converge to a flat metric. So so they use, well, actually, it's not quite, that's not the way they use it. But point is, they use the Kähler-Ricci flow to prove uniformization. Again, if you just start with a complete metric on a non-compact manifold, Kähler-Ricci flow is a very tricky thing. Its uniqueness is not known, or even existence may not be known short term, let alone global existence, long-term existence. So they have to assume curvature decay and maximal volume growth hypothesis. Then the two Chinese mathematicians, Chen and Zhu, have a number of papers on this, and some of their results are very interesting. So, in fact, one of their results is what we sort of was an inspiration for our work. So, they proved that uniformization holds if a certain curvature integral is finite. And interestingly, in the Riemannian or Kähler geometry, it's not that surprising if a certain result holds under maximal volume growth. By the way, when I say maximal volume growth, the manifold we are working with has non-negative Ricci curvature, since bisectional positive implies Ricci positive. So therefore, yeah, Bishop's volume comparison theorem holds. So the volume of such manifolds cannot, volume of a ball of radius r will be less than the volume of the Euclidean ball of the same radius. And by maximal volume growth, one means that the ratio of these two volumes as r goes to infinity is non-zero. So in other words, large geodesic balls roughly have the same volume as a Euclidean ball of the same radius. So that's a very standard assumption. So, but if under that assumption, lots of things happen. So, but these two people showed that in this our setting, even if the volume growth is not maximal, but rather the least possible volume growth, even that leads to uniformization, which is kind of intriguing. And but the intermediate thing is unknown, basically, in between these two extremes. Then, as I was saying, so Gangliu resolved Yau's conjecture in full generality, but again, assuming maximal volume growth. Full generality meaning just positive bisectional curvature and maximal volume growth are the only two assumptions he makes. And then he used this some current tools, the Cheeger-Colding-Tian theory of convergence of Kähler manifolds with Ricci curvature bounded below, etc. And that was a new. So more than the result itself, he introduced new techniques into this field. But the point is that invariably one has had to assume something extra. So our recent result is perhaps the first one where you don't assume make any global assumption or asymptotic assumption. other than, of course, just saying that the underlying metric is complete, which is a global assumption. But on the other hand, we have to work with C2. And in our first paper, we also had to assume an upper bound on the curvature, which is subsequently we were able to remove. So the theorem is that if you have a complete non-compact scalar surface and which has positive and bounded above sectional curvature, then X is biholomorphic to C2. So while this is, as I just said, while this result is only for complex dimension 2 and assumes an upper bound on curvature, it's apparently the first one without any assumption on the global geometry of the manifold. And the proof yields this surprising result that if you have a scalar surface with sectional curvature bounded above, positive sectional curvature without any upper bounds even, then one looks at the Ricci form of the scalar metric and wedge it with itself. So one gets a 4 form on the underlying smooth 4 manifold. And the integral of, it turns out that the integral of that is finite, which is kind of, there's no reason to, a priori, there's no reason to expect this. So first of all, the manifold will have infinite volume, and we are not assuming that the curvature decays or becomes smaller in any way. So why should, but anyway, this is true. But this conjecture, this result itself fits into a general theme that on certain manifolds, the integrals of Ricci curvature, symmetric functions of Ricci curvature should have a prescribed behavior. Which should not blow up too badly. That is the thing. Again, Yao conjectured this. So the main new tool is in the entire proof in Mach's scheme. So one has to basically construct. So in order to ultimately, Mach's scheme involves constructing an embedding of the underlying manifold into projective space or Cn. So one has to construct lots of either holomorphic sections or functions and use them to embed. So in those constructions, the controlling the growth of those functions is crucial. And there one uses a suitable weight. So here, the main insight here is solve a complex Monge-Ampere equation. Both Vamsi and Ved are experts in this. So it was natural to them to consider this approach. So the thing is to solve this complex Monge-Ampere equation on this non-compact manifold. Usually it's done in the compact setting or bounded domains, etc. But here one wants it on the whole manifold. And then construct a global plurisubharmonic weight function. And it's technically it's crucial that it's actually Lipschitz. And other thing important about this is it has finite Monge-Ampere mass. So this the Levy form of the function of the PSH function, if you wedge it n times, you get a top dimensional form, and then if you integrate this, and this result, construction of such a thing is done in all dimensions. So that's why I put n here. And this again uses so it's a novel use of the positive bisectional curvature hypothesis. And but this is not enough. One also needs a PSH under some background exhaustion function. That's where you need positive sectional curvature. That gives us the second condition. So as I said, one controls global analytic quantities, holomorphic sections, and functions in terms of this finite mass weight and gets finite dimensionality, finiteness properties required for embedding into CPN as a quasi-projective variety. So Vamsi and Ved will talk about this scheme in detail. And what's special about dimension 2? Well, the proof itself, various crucial steps. It involves a dimension 2 hypothesis, but even towards the end, if one wants to conclude that the quasi-projective variety is CN, one in dimension 2, the theorem of C.P. Ramanujam that a contractible affine surface that's simply connected at infinity is biholomorphic to Cn. So one ends up using this. Well, so let's see. Then in this minute, let me just briefly explain one new topological obstruction to the existence of B greater than 0 on non-compact manifolds, which we observe. So the result is this: if you have a complete non-compact manifold with B greater than 0, if this is sort of cohomology at infinity, it's sort of, I mean, I won't go into it. It's a direct limit of the cohomology of H1 of X minus K as K varies over compact subsets of M. So if this is a topological assumption we have to make. If this is 0, then the codimension 2 cohomology of X is 0. So in particular, if N is 2 for a surface, it tells us that H2, H lower 2, the homology, the second homology of X is 0. And using that, one can see that, for example, that this Briscoe surface, it's a affine surface in C3 given by this equation. And these objects are well studied. One knows all the homology groups. And then it turns out that this condition is satisfied. H1 infinity is 0 for this. On the other hand, H2 will be an 8-dimensional space. So this one can't admit B greater than 0 matrix, but it's a somewhat, I mean, it's not a big deal. After all, one expects the underlying manifold to be C2. But still, considering that one knows nothing about the topology, so this is a novel observation. So I'll stop here.